So what we're going to be doing is we're going to be doing kind of like what we did before, but with second derivative. All right, so 3.4 has to do with concavity and points of inflection. And this has everything to do with second derivative. So remember how before we found first derivative, we set it equal to 0, we did sign charts. We're going to do something very similar, but with the second derivative. All right, concavity, there's a couple different ways we could define it. Here's the technical definition. If f is differentiable, meaning you can take the derivative, the graph is concave up if, I'm going to make this a little different size. There we go. Okay, f is concave up if f prime is increasing. So remember before we had been talking about f increasing and f prime being positive. Now we're saying that f prime is increasing. So what does that tell us then about f double prime? It could also be increasing. It's positive. So if something is increasing, its derivative is positive. Okay? So now we're bringing in this whole idea of the second derivative being positive. Likewise, if f prime, if we have a concave down part of a graph, f prime is decreasing, which would mean f double prime is negative. And so that's kind of what this next part says. If f prime is increasing, then f double prime is greater than 0, or you could say is positive. And if f prime is decreasing, then f double prime is less than 0. And so that's how we're going to kind of look at this graph of f of x and examine where this graph is concave up and where this graph is concave down. Now, I think the extreme ends of this graph, it's a little bit more obvious. So when I say concave up, I mean it is bent upwards. So over here on the left, we definitely have a concave up piece of graph. Okay? Here's another way we can know it's concave up. All right, if I draw a tangent line, any point along this concave up piece, that tangent line is going to be down here. So we could say that when f is concave up, the graph of f lies above its tangent lines. Okay? So if you ever draw a tangent line and the graph of f is above the tangent line, then that's a concave up piece of graph. Okay, and it's more obvious over here. Now in the middle it's a little weird, and I'll get to that in a minute. Now over here on the right, see how the graph is bent downwards? If we draw a tangent line, it would look something like that. And the graph of f is obviously below the tangent line. All right, so do you see where this graph changes from concave up to concave down? Where do you think it's changing? So there definitely is something weird happening at 0. It's actually changing concavity before 0.
-1.
So maybe -1. Okay, let's talk more about concavity, and then I'm going to ask you that question again.
It switches.
It's not, yeah, so theorem 3.7 is really just a test for concavity. If you have a function where the second derivative exists, if f double prime is positive, then the graph is concave up. And I want you to go ahead and draw a picture of concave up out here and concave down. Concave up is like a cup. Okay, think of it, it could even hold water. Concave down is like a frown. That's a nice way to remember it, although I think the words up and down are pretty descriptive in and of themselves. Okay, so let's think of this idea as it could hold water or water would run right off of it. Okay, so again, this left part could hold water. I'm going to go ahead and put a point here. Look what's happening between -2 and 2. If I drew a tangent line here, would the graph of f be above or below that tangent line?
Above.
No, it would be below. Okay, if I drew a tangent line, it's not curved a whole lot, but it's bent downward, basically. So this is actually concave down, this little piece right here. And that change is happening about -2. Okay, at 0, it's changing again because although from -2 to 0, we're bent downward, look what happens here. We're bent upward again. It's opening up. And where would you say it changes from opening up to opening down? Probably about 2. So if the second derivative is positive for concave up and negative for concave down, what is that second derivative at these points where it's changing from up to down? Or what number comes between positives and negatives? 0. So that's how we're going to apply this theorem. Okay, we're going to figure out where the second derivative is 0. Okay, I'm not talking about where the derivative is 0. I'm talking about the second derivative. Or what normally goes along with 0? Undefined. So this is determine the open intervals on which the graph of f is concave up or concave down. Okay, so let's do the concave up. We've already been practicing writing intervals, so this is just like how it was before. We'd start here and we'd go -infinity until we get to the first point here where it changes. So -infinity to -2, still using parentheses. And then since I'm skipping some numbers, I'm going to do a union and I'm going to pick back up. Again, I'm just doing the x value 0 to 2. Likewise, we can do concave down. What would that interval be? -2 to 0, and union that with 2 to infinity. So I've started with giving you a graph of f. We're going to work our way up to how do we do this when we're not given a graph? Yeah.
Can you like draw the tangent lines on the -2 to 0 and 0 to 2?
Yeah. Let me zoom in a little bit. Okay, so if we wanted to draw the tangent line right here, that would be the tangent line right there.
Oh, I was connecting the 2 points.
Ah, what kind of line would that be?
That's secant.
The secant line. So good question. All right, so I'm gonna go ahead and give a name to these points. These points are going to be called points of inflection. A point of inflection is where the graph changes concavity. And we're going to pretty much abbreviate them as POI. And I'm not so concerned about the x and the y value. Really just what is the x value. So what was our first point of inflection here? -2. And you can make them like really big if you want on your graph. -2. And since I'm going to have many, I'm going to go ahead and write it as a set. -2, 0, and 2. Okay, and at these points of inflection, what do you think the second derivative is? What did we already said it. I'm asking. Or what do you remember?
0.
0. In a general problem, it could be 0 or undefined. Okay, so let's go ahead, turn the page. If you look right here, it's we got another theorem, and it doesn't have a fancy name, so I won't worry too much about it. But it's just theorem 3.8. It's basically saying if you have a point of inflection, then f double prime is 0 or f double prime is undefined. So when I want to determine the points of inflection, that's what I need to do first. I need to find the second derivative, which means start with finding the first derivative. So that would be 4x cubed minus 12x squared. Now, if this had been something we did yesterday or the day before, we would have just worked with the first derivative. But since I want to actually know about points of inflection in concavity, I need to find the second derivative. And in a polynomial, this is pretty easy to do. So that's why we're starting off with this one. So just take the derivative again. Okay, next we want to know where is the second derivative 0 and where is the second derivative undefined. Polynomials, they are nice. They're always defined, so we don't have to worry about this thing. Okay, we will talk about this another day. But for right now, we'll just set this equal to 0 and factor. So this part's going to look a lot like what we have been doing the last couple of days. And then you would just set each part equal to 0 and solve for x. So I get x equals 0, x equals 2. Now when we did this process with first derivative, we called these numbers critical numbers. These are not critical numbers now because this is second derivative. We are going to call these PPOI. What is POI again? Point of inflection. Are y'all laughing because I said PP?
Yes.
So POI is point of inflection. Anybody want to guess what the first P stands for here?
Principal.
Maybe. That wouldn't be bad.
Prominent.
Perfect.
Points.
Okay, let me give you a hint here. I'm not 100% sure. Yeah, I'm not 100% sure these are points of inflection. So I'm going to say P is for possible. Or really, we could say P is for probable. Because remember how with critical numbers, most of the time those numbers ended up being relative maxes and mins. It was only really rare scenarios where it wasn't. And so these are probably going to be points of inflection, but I don't know for sure until I do my number line. Okay, so draw the number line, put your negative infinity in infinity, and put your possible points of inflection. Now,
Are we going to put that double prime in the triple?
we are, not triple, but F double prime, and then up here F.
Oh.
So we're going to test something into F double prime. And remember, it's usually easier to test the factored form. So when you plug a negative number into this 12x, x minus 2, what do you get as a result? A positive. You get a negative times a negative, which is a positive. Now remember before how I drew an arrow going up? Well, that was because I was saying the first derivative is positive, therefore f is increasing. But when the second derivative is positive, f is concave up. Now you could write the words concave up, or you could just draw a little picture. This is there to help you, so you do what you need to do to be able to interpret it in a minute. Okay, probably the next one's going to be negative. Okay, but let's just test it to make sure. Plug in a 1, we get a positive times a negative, and so then we're going to draw a little concave down piece of graph. Okay, what happens when you plug in a number bigger than 2? We get a positive, and it looks something like that. So the graph of f, just to kind of give you an idea of how this helps you, the graph of f is concave up, and then it changes to go concave down, and then it changes to go concave up. Now this is a rough sketch. So this number line is not telling us where the graph is increasing, decreasing, relative maxes or mins. We would have had to use the first derivative to do that. This graph, this little sign chart right here is just telling us about concavity and points of inflection. So let's go ahead and write our answer. So do we have points of inflection? Yes, we do have a point of inflection at x equals 0 and x equals 2. And so you could write it like this. You could write it with the curly braces, however you want. We do need to write a justification statement. Because f double prime changes signs. You don't have to specify, like for 0, changes from positive to negative, and for 2, changes from negative to positive. It doesn't, either way, it's a point of inflection. There's no different name. for these. Okay, what about concave up? What would that interval start with? Negative infinity to 0. So this is very similar to what we had already done. And our justification would be because f double prime is positive. This is the part where you have to be careful and make sure that you're doing the right thing. If you've annotated your sign chart and you've written everything out, you probably won't get confused here. If you try to do all this stuff in your head, you're probably going to get confused. Okay, concave down. That would be 0 to 2. Justification, because f double prime is negative. Okay, and that's how you do these problems. Of course, they could get more difficult. Finding derivative could be more difficult on some problems. Solving for x could be more difficult. You could have undefined, but the process is still the same. Okay, so that's how you do concavity and points of inflection. I'm not going to work a whole bunch of examples because it's very similar to what we already did. I do want to show you, though, another thing that this can be used for. Okay, remember when we had the first derivative test? Anybody remember that? I said this is called the first derivative test because there actually is a second derivative test. And so I don't really care so much that you know the names, okay? But here's why second derivative test is nice. If you have a function where f prime is 0, in other words, you have a critical number. You have a place where the graph levels off, and it could be a relative max or min, okay? Then the second derivative can help you know whether it is a max or a min or neither, okay? So if the second derivative is positive, okay, so let's draw this out here to the side. If the second derivative is positive, that's a concave up piece of graph. Do you see on this concave up piece of graph where the first derivative is 0? It has to be right there, which is a relative min. Okay, so this is a way that second derivative can help you with stuff that we already learned. If you have a second derivative that's negative, that would be a concave down piece of graph. And then if we know that, again, we're counting on the fact that f prime equals 0, then that point is a relative max. Now, if the second derivative is 0, the test fails. And it could fail for different reasons. It could be a point of inflection. There's different things that can happen here. And so you have to be careful, and really, the test fails and you can't use this test. So what I want to do is show you an example that we've already seen, and I want to do it the old way, and then I want to show you how this new test will work. And then I'm going to explain to you there's some types of problems where you have to use the second test. Not because I tell you, but because the first test doesn't work. So let's do example 2 first, the old way. And when I say old way, I mean literally what we did yesterday. Not super old, but not the new stuff. So we have f of x. The old way, we found f prime. And that would be negative 15 x to the 4th plus 15 x squared. And so what would we have done with this yesterday? Factor, set it equal to 0. So I'm going to factor out a negative 15x squared. And then I'm left with x squared minus 1. And then I solve for x. So if I set negative 15x squared equal to 0, that means x is 0. What about this piece? Exactly, x is plus and minus 1, and we called these critical numbers. These are possible relative extrema. Okay, so I'm going to continue doing this the old way, but I'm going to give you just a little indicator. In the new way, what I'm going to do now is I would stop here, and then I would go straight to the second derivative and do something with the second derivative. Okay, but with the old way, we would have a number line, right? And then make sure you list your points, least to greatest. That's always important. Go ahead and test this on your own. This is just a good review of what we did yesterday. Okay, check your answers with what I have up here. And this was one of those scenarios where you had back-to-back pluses. What algebraically is causing the back-to-back pluses?
The flat.
Yeah, the fact that what gave me x equals 0, the fact that that was taken to an even power causes there to be the same behavior on either side of 0. Okay, you don't have to know that. It's helpful, but it can help you like catch mistakes and be able to fill out these charts more efficiently. So here's my big question. Do I have a relative min?
Yes.
Yeah, and it's happening at x equals -1. And I'm not going to write the justification on these just because I really want to get to the next part here. And I have a relative max happening at x equals 1. And I know that this is the answer. These are the relative extrema. So when I do this a second way, I should be able to get the exact same answers. What is happening at x equals 0? A max or a min?
A saddle point.
Neither. A saddle point. Okay. So, and that's because there's no change from plus to minus. All right, so watch what we're going to do now. I'm going to solve this a separate way, keeping in mind that there are times when you have to do it the second way. Not because I tell you, but out of necessity. I'll talk about that in a minute. For now, let's just see how the process works. Okay, so what you're going to do in the second way is you're first going to find the second derivative. So maybe I should write new way right here. So the second derivative would be -60x cubed plus 30x squared, or 30x, sorry. And we're going to take our critical numbers and we're going to plug them in to the second derivative. Okay? In other words, I'm going to do f double prime, and I'll just start least to greatest. F double prime of -1. And I'm going to calculate this. If the result is positive or negative, that will then tell me if that is a min or a max. I already know it's a min, so I should get that same result. If I plug -1 in here, I have -60 times -1 cubed plus 30 times -1. And you don't really have to crunch all these numbers, but you need to do enough to figure out if this thing is positive or negative. So -1 cubed would be negative, times -60 would be positive. So this whole result would be positive, right? So according to the second derivative test, if f prime equals 0, if we have a critical number here, and when I plug that into the second derivative, I get positive, that indicates concave up, which means there is a relative min happening at that x value. It's the same thing I got over here. It's just another way of confirming it or doing it. Okay, let's test 1. So that'd be negative 61. What about this result? Negative, right? So if the second derivative is negative at x equals 1, that means concave down. And you can even just tell by the picture, that's a relative max. So this is not something you have to memorize. It's really something you can draw and figure out. And then we're going to see the test fail here at 0, because when you plug in 0, what do you get in return? 0. So the test fails. Meaning, I don't know what's happening at x equals 0.
So you first have to take first derivative, find your critical numbers, and then take second.
Exactly. Now, if I just give you an f of x, this is probably, like what I've done here in green, is probably not the way you're going to want to do relative extreme. You're probably going to want to do it the way we've already done it. This is a nice way to check your work, for one. Let's fill in the blanks here, and then I want to show you a couple of examples of where you have to use second derivative. So this kind of wraps up what we said. If the graph of f is concave up, so you can even just draw a little picture, the place where f prime is 0, that right there, that x value, gives you a relative, and you can just look at the picture. Oh, it's a min, it's the smallest point. Likewise, concave down, that would be a relative max. All right, so let me show you an example of when you definitely need the new way. I'm going to do this example, if you turn the page, I'm going to do this example tomorrow. I know some of you won't be here, but I want to show you something really quick, and then I'll go over it again tomorrow, probably in, more detail. I want you to look right here at this. Okay, I don't have an equation. I don't know a lot about this function. But I know when x is 2, the y value is 5, the derivative or slope is 0, and f double prime is negative. By second derivative test, what do we have at the point 2, 5? A relative min or a relative max? A negative second derivative and a 0 first derivative. This is what second derivative test tells us. That gives us a relative max. That's all this is where this would be the easiest way to do this problem. In fact, you really can't do it another way. Like some people may say, oh, but first derivative is changing positive to negative. But what I don't know is that maybe at 1.5, the slope turns down to -2. I don't know what's happening between 1 and 2. So this is a great example of where second derivative test is easier, and the first derivative test may not even, you don't really have enough information to do it anyway. Okay? So that's one example. Okay, I'm going to go over that tomorrow in a lot slower and more detail. But I just kind of wanted to give you an example of when you might need that. Okay, I want you to turn the page and look at the 3.4 worksheet, because this is part of your homework. You're going to have some book work and then this. On this, we have an open-ended part of our problem, and they're at some point going to ask us about a relative max or min. Okay, but look at what the type of problem we're dealing with is. Implicit. We have not done sign charts with implicit. This is 2 variables. We actually can't make a sign chart with this. Okay? There is a way to kind of force that stuff to work, but it's so much easier to use second derivative test here. All right, so you may want to make yourself a little note here, because this is going to be part of the homework. And we'll go over it. When you do the homework, I just want you to attempt the problems, give you like a good attempt.